Cyberknife. Before starting the presentation, I am Yiğit Akbey and I will give general information about Cyberknife. Next, Aylin Ceren Güven explain Cyberknife technology and its equipments. Later, Mustafa Özkan Orhan will give information about the treatment process. Finally, Sena Bal will talk about monitoring and equipment room and the advantages of Cyberknife. Before I start talking about Cyberknife, I'd like to talk about radiosurgery, which is the basis of Cyberknife. Radiosurgery is surgery which using radiation to distraction of tissue areas that are precisely selected using ionizing radiation instead of excision with a knife. Like other forms of radiation therapy, it is used to treat cancer. Although surgery is said radiosurgery does not include real surgery. Instead, highly focused radiation beams are used to treat cancerous tissues without a surgical incisions or opening. Now I will give general information about Cyberknife. The Cyberknife system is a non-invasive treatment for cancerous and non-cancerous tumors and other conditions where radiation therapy is indicated. It is used to treat conditions in the body including the prostate, lung, brain, spine, head and neck, liver, pancreas and kidney, and can be an alternative to surgery or patients with non-operative or surgically complex tumor. Cyberknife treatments are typically performed in 1 to 5 sessions. The Cyberknife system has over 20 years of clinical evidence and has helped thousands of cancer patients. Now I will talk about the structure of Cyberknife. Cyberknife consists of a lightweight linear accelerator mounted on a robotic arm. Besides the robotic arm, there is a camera group that displays the room from every angle, a patient bed, and a control panel where we can control all these technical devices. Also, we will give more detail next slides. Now I will talk about working principle. Near real-time images allow for the patient's movement tracking within 1 mm spatial accuracy. The Cyberknife references the positions of the treatment target to internal radiographic features such as the skull, bony landmarks, or implanted fiducials rather than a frame. The Cyberknife uses real-time X-rays to establish the position of the lesion during treatment and dynamically brings the radiation beam into alignment with the observed positions of the treatment target. The Cyberknife aims each beam independently. When the target moves, the process detects the change and accommodates it. Better for which patients? This treatment system has been used to successfully treat lesions in the patients who are otherwise not candidates for surgery or for lesions that are not amenable to open surgical techniques.
Cyberknife technology. The Cyberknife radiosurgery system is a device designated for cancer treatment. Mainly it is comprised of a linear accelerator, produces 6 MV X-rays positioned on an industrial robot with 6 joints, and a robotic patient bed that can move in 6 directions. The robot has a sensitivity of 0.2. The Cyberknife hits tumors with radiation very sensitively with the combination of determining target and the controlled robot system. The Cyberknife system are divided into three: imaging system, respiratory tracking system, robotic delivery system. Robotic delivery system. The robotic delivery system consists of a linear accelerator, manipulator, and robocoach system. The robot is KUKA, which is commonly used also in car industry. This model is, however, extensively modified to work as a medical device for radiotherapy. The robot is highly accurate, with capable of hitting a moving target 0.5 mm accuracy. The high accuracy, together with multiple beam delivery directions, enable to treat confidentially small targets at difficult positions. Linear accelerator. The Cyberknife linear accelerator produces a photon beam of 6 MV nominal energy. The compact, lightweight Linac head is attached to the end of the robotic arm that is free to rotate and translate with 6 degrees of freedom. As a result, treatments are non-isocentric, allowing for unique beam angles and orientations. High dose output supports efficient treatment delivery. And manipulator. Manipulator 6-axis mounted on a pedestal at the head of patient area provides uniquely able to follow targets through the full range of motion with sub-millimeter accuracy and precision. The robocoach system provides a highly flexible 6 degrees of freedom mechanism for automatically positioning. The combination of the robocoach system and the robotic manipulator for Linac positioning enables the Cyberknife treatment delivery system to deliver those precisely and to the right location automatically. The upper manipulator arm between axis A2 and A3 integrates a contact sensor on its outer surface, and each step is triggered if an object comes in contact with it. The robocoach system has 5 rotational axes and 1 linear axis. Imaging system. The Cyberknife will locate its target by comparing patients to the images from the treatment planning system to the images taken from the patient before and during the treatment. These treatment images are taken with an integrated X-ray imaging system. The system consists of 2 X-ray sources at the ceiling and 2 large digital image detectors embedded at the floor. The Cyberknife system utilizes live image guidance, and if the patient or the target moves during the treatment session, this will be detected and corrected by changing the direction of the robot or moving the robotic coach on where patient lies. The system consists of 2 X-ray sources at the ceiling and 2 large digital image detectors embedded at the floor. X-ray sources. The Cyberknife uses stereoscopic X-ray imaging for patient alignment and motion compensation during radiation therapy. The X-ray sources are attached to the ceiling at 45 angle to both sides of the treatment table. It has a 2.5 mm equivalent thickness aluminum filter. X-ray generators provide high voltage power to X-ray sources. X-ray generators can be found in the treatment room or equipment room. Image detectors. They are used in conjunction with the X-ray sources to confirm the patient's position for treatment. It is mounted on the ground on both sides of the treatment table, perpendicular to X-ray sources, at the 45-degree angle with the concentric. And there is a camera system on the floor that can take digital images. The synchronous respiratory tracking system tracks the respiratory movement with an optical camera and synchronizes treatment beam delivery targets. This system enables the robot to move with the target and irradiating it during the breathing pattern in real time. This synchronous system calculates an individual breathing pattern by utilizing 3 cameras and a LED light fixed in a synchrony vest, which the patient wears during the treatment. with the cameras tracking the movement of the chest wall and simultaneously the X-ray imaging system tracking the target. The Cyberknife's computer system is able to calculate a predictive model of the patient's breathing cycle. The model is used to predict in 10 milliseconds beforehand where the patient will be in every phase of the breathing cycle. The model is constantly updated during the treatment, so if the breathing pattern changes, it will be observed and taken into account. If there is an unpredicted movement, treatment will stop immediately. This synchronous system is easier for the patients because they can breathe normally during the treatment. The synchronous system used in conjunction with the following target tracking methods: fiducial tracking, excite lung tracking, excite spine tracking, and 6D skull tracking. 6D skull tracking uses bony anatomy to track intracranial targets and automatically correct for even the slightest translational or rotational shift that might occur during treatment delivery. Excite spine tracking system eliminates the need for surgical implantation of fiducials by using the bony anatomy of the spine to automatically locate and track tumors, making radiosurgery more precise and less invasive. 6D fiducial tracking. For extracranial lesions, targets can be tracked in soft tissue through the use of fiducials. Excite lung tracking system directly tracks the movement of lung tumors without fiducials while maintaining precision. Delivering Cyberknife radiotherapy. Cyberknife radiotherapy treatments are delivered with hundreds of small photon beams. The radiation beam diameter is changed with a collimator. The robot can change the size of a collimator where faced with an iris collimator by reducing and increasing the opening. With some treatments, only few beam sizes are needed, so iris is not needed. Robot can then pick up a suitable fixed collimator from exchange table next to the robot. This is done automatically even during the treatment. The Cyberknife system offers a collection of available collimators, providing the versatility needed to treat a wide range of clinical indications from trigeminal neuralgia to large tumors. One of them fixed circular collimators, others iris variable aperture collimator, Insize 2 multi-leaf collimator.
Cyberknife does not only consist of parts in the treatment room. There are also parts where the device is managed, modulated, and monitored. Cyberknife Treatment Monitoring Room. All stages of treatment are planned and monitored in this room. There are screens where real-time images from X-ray detectors are compared with CT images. The image of the patient in the treatment room is followed here by engineers and healthcare staff. Another part is Cyberknife Equipment Room. There are power distribution units and robot controllers here. The chiller and an air compressor associated with the chiller, which are used to cool the high heat generated in the X-ray tubes, form the mechanical part. Advanced magnetron modulator part includes pieces such as gun driver and modulator, which provides high voltage pulses. And there is also a computer part with many workstations. Before explaining how Cyberknife treatment steps are done, I want to compare Cyberknife with other radiotherapy and radiosurgery techniques and explain some of its advantages. Comparison of conventional radiation therapy and Cyberknife. General linear accelerators are examples of conventional radiation therapy. The X-rays produced by the conventional linear accelerators are applied to the patient around the isocenter created by the intersection of the axis of the gantry and the axis of the collimator. Here it is essential to fix the patient. But on the other hand, Cyberknife monitors the patient's movement instead of fixing the patient. There is no fixed isocenter. Unlike the conventional radiation machines, the Cyberknife literally can dance around the room. Those radiation beams can come in from the head of the patient, the feet of the patient, besides at multiple different angles. That's something the conventional radiation machines, which are fixed, are not capable of doing. And as a result of that, we can get very high doses into the tumor and spare the normal tissue surrounding it. Comparison of Gamma knife and Cyberknife. Gamma knife is a stereotactic radiosurgery procedure that ensures the destruction of diseased brain tissue with coordinated gamma rays. The principal differences between Gamma knife and Cyberknife is that Gamma knife requires a large metal frame being mounted onto the patient's head with scraps before and during treatment. Cyberknife is non-invasive and pain-free treatment that allows patients to lie comfortably on a treatment couch while the system moves quickly around them. Cyberknife patients require no general or local anesthesia during the procedure, unlike Gamma knives. Cyberknife is a dedicated robotic system that can approach a tumor in the brain, head, neck and spine from over 1,300 positions with pinpoint sub-millimeter accuracy. Gamma knife is a gantry design system that's limited to approximately 201 positions. Gamma knife can only target brain or cervical spine cancer with a single treatment of high-dose radiation, while Cyberknife is able to treat cancer anywhere on the body in 1 to 5 radiation treatments. Clinical studies have shown that certain tumors and conditions treated with a lower dose of radiation for 2 to 5 treatments is better for surrounding healthy organs and tissues. Unlike Gamma knife and other conventional radiation therapy types, Cyberknife stands out with its usage in the treatment of tumors and cancer tissues in the moving organs and risky areas, like intracranial tumors, head and neck tumors, spinal cord tumors, lung cancer and lung tumors, and prostate cancer and prostate tumors.
Now, I'm gonna tell you Cyberknife treatment process. Cyberknife treatment process can be divided into 5 steps in general. Initial consultation, treatment setup, treatment planning, treatment delivery, and follow-up. Let's examine these steps in detail now. This is an example for Cyberknife treatment process. Explains the individual steps. It's a table shows how long each step requires, the teams involved in each step, and what to do at each step. Initial consultation. The initial consultation involves the radiation oncologist, a surgeon, and other physicians if required. They will determine if Cyberknife is right for you. During your consultation, the procedure, as well as the risks and benefits, will be explained to you in detail. If treatment is to be done on soft tissue, small gold markers, known as fiducials, will need to be implanted into the tumor-bearing region. Doctor will discuss the fiducial placement procedure with you if it's a necessary part of your care. A list of all medications that is used by patient should be brought to these appointments. Treatment setup. Treatment setup consists of 3 parts: imaging, making a mask or body mold, and fiducial placement. Firstly, imaging. A special CT scan called CT simulation is acquired for every patient, and a MRI, if needed, is also acquired. Physicians use the scans to identify the size, shape, and location of the lesion or tumor, along with the surrounding vital structures to be avoided. Secondly, making a mask or body mold. Depending on the need for treatment, a custom soft mask or body mold is formed and used to minimize movement during the treatment and ensure your comfort. The process is simple and painless. Thirdly, fiducial placement. The treatment of body tumor using the Cyberknife system requires the implantation of gold seeds, referred to as fiducial markers. These fiducial markers require the short outpatient procedure to implant 3-6 seeds in around the tumor. This will enable Cyberknife system to track the tumor throughout the treatment. Lesions in the head and spine do not need this placement. In most cases, fiducial placements will be done as an outpatient in a radiology facility, and you will be able to return home within an hour or two. Prostate fiducials will typically be placed under ultrasound guidance, either the urologist or by the radiation oncologist. Placement of CT-guided lung fiducials may require a hospital-based radiology department because some of the placements may result in a complication. Other fiducial placement methods may also be used, such as placing them through the scopeaces through the bronchus or esophagus. Treatment planning. Previously obtained CT and MRI data are sent to the Cyberknife treatment planning computer, where the physician's team will use advanced software to customize the radiation beams that the robot will deliver to the tumor or lesion during this treatment. Planning considerations include exact tumor or lesion configuration and its relationship to adjacent normal body structures, which in turn influences the number, intensity, and direction of the radiation beams that the robotic arm will send to the tumor. This will help ensure that a sufficient dose is administered to the tumor in order to destroy it, while minimizing to the greatest degree possible the radiation dose to the adjacent normal tissue. Then I will explain this in more detail with steps. Treatment delivery. Treatment delivery consists of 4 steps. First of all, arriving. Wear comfortable clothing and no jewelry. You may bring your favorite music CD to listen to during the treatment. Try to relax knowing this will be a painless procedure. Feel free to bring a list of questions to ask the Cyberknife team. Then, positioning. You will be asked to lie on the treatment table and will be fitted with the custom mask or body mold made for you earlier during the setup process. In some cases, a mild sedative will be given to you help you relax, along with any other medication that may be needed during treatment. In some cases, anesthesia may be required. This evaluation will be done prior to treatment. Third and main stage is treatment. During treatment, you will need to lie still. You may sleep during the procedure. The length of treatment varies depending on the location of your tumor. The image guidance system periodically compares X-ray image to the CT scan to ensure the radiation is targeted accurately at the tumor. The imaging system acquires the first set of X-rays in the treatment position. The table then adjusts to provide the necessary millimeter alignment, and the robotic arm then moves the linear accelerator to its first position and delivers the first treatment beam. This process is repeated many times as the X-ray system reacquires the target and the robotic arm realigns the linear accelerator from multiple different positions, often greater than 100 times. At each angle, the precise radiation beam is delivered. The image guidance system utilizes bunny-lead markers or implanted fiducial markers to track the exact location of the tumor during the entire treatment process, creating an extremely accurate and precise radiation treatment procedure. If a lung or upper abdominal tumor is treated, the breathing cycle is also continuously tracked and correlated with tumor position, causing the robotic arm to assume a real-time breathing pattern that tracks the tumor. This robotic breathing pattern exactly follows the tumor as it moves through the breathing cycle, keeping the radiation beam squarely on the tumor throughout the entire treatment. The entire process is painless and usually lasts 30 minutes or 2 hours. Fourth part is completion. When your treatment session is completed, our nursing staff will do an assessment. When the nursing assessment has been completed, you will be released to home and may resume normal activity within 24 hours. Your physician will prescribe between 1 to 5 treatments. To maximize your healing, we might insert rest days between the treatment days, depending on the treatment site. If the treatment plan calls for more than one treatment sessions, known as fractionated cyberknife treatment, the radiation therapist will schedule all of the appointment times with you. Final part is follow-up. As with any radiosurgery or radiation therapy procedure, the progress is likely to be monitored by follow-up exams and imaging. Patients will be given appointments to follow up with the radiation oncologist and surgeon to see how patient is doing and will. Follow-up imaging is generally performed to monitor the tumor's response to treatment, though the exact studies and their timing will vary with each situation as determined by the participating doctors. Now I'm gonna tell treatment planning steps. 1. Identify the treatment site. Each anatomical location has a predetermined group of nodes that are considered a good selection for that site. 2. Select single isocenter, multi-isocenter, or a non-isocentric plan. Single isocenter used for delivery of a spherical region of high dose. Multi-isocenter used for a ball-packing approach. Non-isocentric technique is used most commonly due to greater flexibility. 3. Select the size of the collimators. For most cases, a collimator diameter is chosen that is equal to approximately 75% of the lesion's smallest projected cross-section. And 4. Define the treatment goals. Run the inverse planning software. Cyberknife's LP-based optimization. No dose volume constraints. Hard constraints may lead to an infeasible solution requiring the user to increase the range of allowable dose to tumor, increase the maximum dose allowed to critical structures, reduce constraint weights, repeat until a solution is found. New sequential optimization. Acquire New provides a scripting approach where the users can prioritize the treatment goals. A series of optimizations are run in succession with one new goal at a time. This approach always guarantees a feasible solution. Cyberknife inverse planning algorithm uses linear programming. Linear programming is a procedure for finding the maximum or minimum of a linear function where the arguments are subject to linear constraints. The simple method is one well-known algorithm. Cyberknife immobilization and tracking. There is two lesions, intracranial and extracranial. Intracranial lesions, immobilization with aqueous mask. Patient's positioning is monitored using body landmarks. For extracranial lesions, immobilization with vacuum bag, patient positioning is monitored using either implanted visual markers, spinal cord anatomy, and lung tumor silhouette. And these are steps of computer programming. 1. Identify the treatment site. 2. Setting the planning goal. And 3. Neosecondal optimization. This is a prostate and this is a clinical result HDR-like prostate plan. You will see such a plan at the end of the planning steps. And there is a 4 Cyberknife tracking techniques: skull tracking, visual tracking, spine tracking based on bony anatomy, tracking of lung tumor slate. Now see the pictures of skull and visual tracking. And these are the X-side spine and X-side lung tracking system. Thank you for listening us.